Hi everybody. Today we're going to look at how to create a slope field, which is technically the graph of the solution family of a differential equation. Remember, when you solve a general or come up with a general solution for a differential equation, you are finding an entire family of solutions that all have the same derivative. They just potentially differ by a constant. So that's it. A slope field is a graph of the family of solutions to any differential equation. And the cool thing about these graphs is that they're not continuous graphs like we're used to. They're actually like the math equivalent of an impressionist painting where you have a bunch of little dots that when you stand back at a far enough distance and you look at them, you can see some picture created. And the picture is the family of parent functions. Here's some examples of slope fields, all right? And you can sort of see the general shape going through there. This would be a slope field for a sine graph, y equals sine of x. Here's another one. This would be potentially an odd degree polynomial function with a positive leading coefficient. All right? Here, something that has a vertical asymptote at x equals 0. This would be a constant solution. All right? So to create one, it's fairly easy. You just have to figure out what the slope of the tangent is at a series of points, and then you're going to draw a small little line segment, a small piece of the tangent line that matches that slope, that has that slope. So you'll see the slope field questions don't give you the standard grid with the vertical and horizontal grid lines. They'll give you these points. And the points represent all the places where they want you to draw a little piece of a tangent line. So each of these points has traditional coordinates like it would be at the corner of a box, right, on a grid line, on a coordinate axis system. So there's 1, 0 right there, x equals 1, y equals 0, but you could put coordinates of points in any one of these places here. So let's focus in on that 1, 0 thing again. And what you're going to technically do here is you're taking the derivative, which is given to you, dy dx equals x plus 1. Remember, the derivative tells you how to find the slope of the tangent line. And we substitute in our coordinates. Now, there's no letter y to substitute into here, but there's an x. So when I substitute 1 in for x, I wind up with a slope of 2. So I draw a little piece of a tangent line that would have a slope of 2. And you should know that's pretty easy. You can just aim for the points here, right? A slope of 2 would be technically, if I was starting down here, I'd be going up 2 to here and then over 1. So I'd be aiming for that point and I'd be looking for a slope that matched that. All right, and that's really what you're doing here. So I've put together the slopes for all of them here because there's a lot of points. It is a little tedious, but it's not hard. So here's what it would look like. Now, I don't know if you can see it in there. Like I said, it's a bit of an impressionist painting, but the solution to this system, if you were to anti-differentiate x plus 1 dx, would be 1/2 x squared plus x plus a constant of integration. So you have this family of parabolas opening up, and I hope you can see that within the slope field here. You've got a parabola there opening up, a parabola there, a parabola there. There, they all just differ by a constant, right? And the slope field, all of those little tangent line pieces, when you step back and you look at what picture they're creating, will show you the behavior of the family of parent functions there. So just a little practice here. There's one from a former AP question. They give you the derivative there. In this case, it has both x and y. So if you were to take one point on here, the point 1, 1, and you substitute y equals 1 and x equals 1 in, you'd wind up with 0 divided by 1, or 0. So a slope of 0 means your tangent line piece would be horizontal. If you want to try to figure out what the others would be, you can pause the video for a moment and try this out. I'm going to show you the solution in a second. Okay, here's the solution, and you're estimating. No one's asking you to come up with, the perfect slope there. You're, doing your best guess at what the steepness of the line would be, whether it's going up or down based on a positive or negative slope, whether it's horizontal. What you should be doing is you should be consistent. All right, everywhere the slope is 2, your little tangent line pieces should look the same. They should essentially be parallel to each other. All right. Here's another example here with x and y. I'm not going to go through the whole thing. It's not really necessary, but you can start to see where we're going to head with this. They're going to graph a slope field, which will give us some idea of what the family of parent functions look like, and that's a general solution, the entire family. And then a second part of the question will be to find a particular solution when they give us some initial condition. That's a point on the parent function, the one parent function out of the family that they want to talk about. That's the idea. All right, so besides drawing slope fields, there's other questions you might be asked where you're trying to match, right? So there's 2 real categories that these things fall into. You can try to match your slope field to a differential equation, right? And if that's the case, you're using the coordinates of points to determine whether the slopes at the tangent pieces are correct by substituting the coordinates into the derivative. If you have to match to a parent function, that's a little bit easier. You're just seeing which slope field looks like what the parent function family would look like, and you'll see a couple of examples of that in a second. So let's start off with differential equations. Here they are. You can see the equations down at the bottom. I just want to show you some tricks that you can follow along as you're trying to look to see whether these things match. In this first one, question number 15, notice there's no y in the derivative. That means the y-coordinate will never affect the tangent line slope. Never, because it's not even in the derivative, so only the x will change it. So the slopes are only going to change as you move from one x value to another. So the shortcut there is that your tangents are all going to be parallel to each other along vertical lines, and this one would be choice B. There's a similar shortcut that works if there's no x in your derivative. That means the x-coordinate doesn't affect the slope of the tangent line. So your tangent lines will all be the same at the same y value. So along horizontal lines, your tangents will be parallel. Number 17 and 18, when you have both x and y in, what you do is you start looking for some obvious things. Look for horizontal tangents, because those have slopes of 0, and a slope of 0, right? You can just figure out by substituting coordinates of points in to see whether or not your derivative is equal to 0. In this case, that would be here. And then, of course, process of elimination, number 18 would be A. The other category of slope fields are when you're matching them to a parent function. So you notice there's no dy dx over here on the right. These are the parent functions. Now, these are specific ones or particular solutions, but the family of them, or the picture, the slope field picture of the family of parent functions, should be able to be present or just apparent to you as you're looking at each equation. So let's look at number 7, y equals 1. That's a constant function, horizontal lines. Look for the slope field that matches that. That's an obvious part D. Question, number 8, y equals x. You know what that line looks like, so find y equals x, slope field. All right, it's going to be that 45-degree angle going up from the bottom left to the top right. There it is. Number 9, y equals x squared. You're looking for parabolas that have the y-axis as an axis of symmetry and are opening up, and that would be C. All right, number 10, you're looking for a cubic polynomial with with a positive leading coefficient. So that's going to be increasing as it goes from left to right. It's going to level off around the middle there, and that's F. Really take a minute to kind of step back and look at the slope field through the eyes of someone admiring an impressionist painting, because that's essentially what you're looking at here. I'm going to skip number 11 right now, but just for future reference, number 11 would have a vertical asymptote at x equals 0, and there's only a couple that fit that, A and G. But let's go on to sine of x. Remember, that starts at the midline and goes up to the maximum and then down again, and that's really choice E. Cosine of x is going to start at your maximum, so that's going to be choice B. Natural log of x technically is asymptotic to the negative y-axis, and then it curves to the right as it crosses over the x-axis, and that one's going to be choice G. So process of elimination, the rational function y equals 1 over x squared has to be choice A. Now, again, They're tedious, but they're not hard to create. So you're going to see as we start doing AP questions that have slope fields in them, you don't really get a lot of points for a slope field because they're so basic to do. The bulk of the raw points from those free response questions is going to come from the later parts where you're finding particular solutions. All right. I hope that makes sense to you. And of course, feel free to rewatch the video as many times as you need to.